Okay, so welcome everyone. Today I'm going to be discussing a system that I've been working on for a few years called Stateright. This is a model checker that's provided as a library in the Rust programming language. And this talk covers quite a lot of ground. If you really want to go into kind of learn the specifics of the system, I highly recommend the book, which is available at www.stateright.rs. So I'll start with what this talk wants to cover. The first thing I want to discuss is what makes distributed systems difficult. Then I'll discuss some techniques that the industry uses to help manage those difficulties, along with some limitations of those techniques. And then I'll discuss Stateright and sort of its approach to addressing some of those limitations. And then just to preview sort of some of the answers to these, race conditions and non-determinism are what make things difficult. Chaos testing and model checking are two example techniques that have proven effective. And the idea behind Stateright is to embed your model checker into your code so that you can verify sort of final production implementations. So if we focus on sort of what makes distributed systems difficult. The reason you might distribute is one reason is you might want to improve the performance of a system. And another reason might be that you want to improve the availability of the system. And in doing so, you introduce non-determinism. So for one, time is no longer, you can no longer count on time being sort of a total order. My n nanoseconds since Unix epoch is not going to necessarily match exactly yours. And so there is no notion of now in a distributed system. Rather, we have a total ordering on our own clocks, perhaps as long as our clocks can't sort of go backwards in time, et cetera. And there's some caveats there. But to actually establish an ordering between two different systems, generally speaking, you need to perhaps send a message. So I can send a message to another node on the system, and that establishes a happens before relationship. So it must be the case that I sent the message before you received it. And generally speaking, that's how I like to think about a distributed system, that it's more about the events than the time. I do know that you can, there was a recent talk about leveraging atomic clocks to help put sort of probabilistic upper bounds on the deviation between times. So that's also an effective technique, but just generally speaking, I like to think of time as a partial order within the system. And that makes things a little bit more complicated. Nodes can crash. So a distributed system, if you built a distributed system to improve availability, then generally speaking, the assumption is that even if a node crashes, the system should continue to run. And that's perhaps not a property that you would normally have in a non-distributed system. You can get timeouts when you're communicating with other nodes, and sort of what happened is indeterminate. I think a particularly interesting thing about a distributed system is that you generally don't want to stop the world. Again, kind of speaking to the availability characteristics. You can't stop the world to do an upgrade. So when you do a rolling deployment, you have different versions of the code running at any given time. And this can even get more sort of insidious than that. You might have a really large distributed system where at any point in time, you might expect particular nodes to be unavailable because you have hundreds of thousands or even millions of nodes. And so a node might be shut down, and so it hasn't gotten the latest version, or it might be behind a switch that's had a problem, and a data center technician one day repairs that switch, and all of a sudden a node running code from 2 years ago comes online. And what are the implications of running really old code? We won't talk too much about this use case, but it's just something to bear in mind. Messages can be reordered. So the internet is full of redundant paths, or even within a data center. And so if I send two messages, just like if I send two letters in the mail, those messages can land in different orders, even if I'm sending them to the same destination. So what are the implications of that? Messages can be lost in transit. And if I don't get back a reply, I don't know whether the message was lost in transit, or maybe it was it was delivered to the node that I'm speaking with, but it wasn't able to reply, or maybe it crashed after it processed my message. And so what happened, typically what will happen is I'll retry that send, and it's possible that the message gets delivered twice in that scenario, or it's even possible that I didn't do a retry, but the network devices resent a packet, resulting in message redelivery. And then another thing is large distributed systems are kind of a target of attack. So security vulnerabilities in these can be even more perhaps problematic than a security vulnerability on a smaller sort of localized system. Now, I'm not going to talk about security vulnerabilities either. This isn't really my area of expertise, but I think this is something that's worth exploring with regard to Stateright perhaps in the future. And to kind of demonstrate this, the non-determinism, imagine a system where two different clients make requests to a service. And this is actually a simplified diagram, and I'll elaborate on what this omits. So the first decision is, does the service reply to the first client's request or the second client's request, or does it time out? If it replies to the first client's request, then there's a second decision, which is, does it reply to the second client's request next, or does the second client time out? And so on. And so that sort of shows you how non-determinism now turns your program into this, not just a decision tree, but it's a decision tree where you don't have control over these decisions, and sort of probability will sort of dictate what actually happens at any given time. And this, I mentioned, is a simplification because here where I show that both nodes time out, or rather both requests time out in the upper right, it's possible that they both think that the request timed out, but maybe it landed on the servers and they just didn't get a response. Similarly, for some of these where let's say this one down here where the second client times out, it's possible that the client timed out, but the server did handle the request. So again, the amount of branching here is can increase very rapidly. And that's what makes these hard to sort of reason about. So now we'll talk about techniques that are effective at addressing some of this non-determinism. And the general theme here is that you have to exercise the non-determinism in a more exhaustive manner than you might do with a typical unit test. Because a typical unit test might only exercise what we call one trace of the system, which is to say one sort of sequence of steps in that tree. And it might not explore other branches because it's not perhaps exercising every single possible fault or every interleaving of possible scenarios. One system that's been incredibly effective is Jepson, which is developed by Kyle Kingsbury. And Jepson does what you might call black box testing of the sort of resulting binaries. What it does is it will perform requests to this system and record what it's doing. And then sort of concurrently with that, it will crash nodes, it will introduce network partitions, it will alter the clocks on the nodes, and see how the system behaves in response to that. And then you can test various expectations of the system. So a very common expectation is that the system is linearizable. In a nutshell, linearizability indicates that a system behaves like a reference sort of single-threaded implementation, wherein you might say, a computer, a single-threaded queue might be your sort of reference implementation. So you might say the system should behave just like a single-threaded queue would, which is to say that if I add something to the queue and then add a second thing to the queue and then I dequeue, I should observe the first thing that I added, and then if I dequeue again, I should observe the second thing that I added, and I shouldn't see like stale values, etc. So that's sort of linearizability in a nutshell. And I guess another important aspect of this is by thinking about a system in having a reference sort of single-threaded implementation, you can reason about preconditions and postconditions for each operation that you're invoking on that system. So Kyle has tested dozens of real-world systems, and he publishes these on his website, which you can find Jepson.io. And most of them have failed. So they've failed to respect linearizability or other properties that they've claimed that the system should exhibit. So this is just tremendously successful. I highly recommend looking into Jepson. The sort of limitations of Jepson are that it only tests a random subset of possible traces. So you can do you can exercise a system for hours, days, months within Jepson, and still not necessarily flesh out all the bugs that can happen even within perhaps 20 steps, right? Just because the possible permutations are so large, the permutations of how the system can evolve. So this is not to dissuade you from using Jepson. I would actually say this is probably one of the best tools available, but it's just important to know, what are the limitations here. Another technique is actually proving that your system is correct. So when you prove a system is correct, you make some sort of claim about the initial state of the system, and then you make an inductive argument, generally speaking, to say that every next state preserves that invariant. And I guess there's other ways to, other kinds of proofs, but this is a key approach. Generally speaking, proofs would target a design of the system, but there is some precedent for testing implementations of systems. One major limitation of proving a system is that it requires quite a lot of training. It is very time consuming, generally speaking. And so I think that's perhaps the two key limitations here. For a really fantastic paper on a sort of a real world implementation that has proofs of correctness, in the distributed system space, I recommend this paper, Iron Fleet. And another technique is what's called model checking. So earlier I showed you that slide that sort of enumerated a high-level model of a particular system where there's two clients and they're sending messages to the system. Model checking, basically, the goal there is to visit every single one of those states in that diagram. And oftentimes, though, you do have to put some boundary. So you might say, well, every state that's reachable within n steps, or some other kind of boundary. But by approaching the problem in this way, you can say with confidence that for all cases where X holds, my properties also hold. So it gives you it's a more systematic kind of testing. Now, typically, model checking, because it has to enumerate these huge state spaces that grow exponentially, they typically target designs of systems and not the actual final implementation. And so one approach is this language called TLA+, which has a model checker called TLC. And you can't actually run TLA+ code, in production to take customer requests. It serves more as a blueprint. And Leslie Lamport has this great write-up called "Who Builds a House Without Drawing Blueprints?" to address this, potential criticism that, well, I don't want a blueprint. I want to test my final implementation. And he points out, houses, if you build a house, you would start with a blueprint, and you can't live in the blueprint. But that doesn't mean that a blueprint's not useful. Certainly a blueprint can tell you if the house, isn't buildable, right? It doesn't mean that you're going to build the house perfectly, but certainly creating a blueprint ahead of time makes sure that you don't do something completely crazy. And that's sort of the approach that many of these model checkers take, including TLA+. But of course, the natural limitation here is that there's a risk of the implementation diverging from the design that you've demonstrated to be correct. A fantastic paper in this regard came out of Amazon, and it's about using TLA+ and the TLC model checker for checking AWS services such as S3, DynamoDB, and I think some other services. All right, so now that we've discussed some techniques that are sort of well established, I'll talk about some techniques that are not quite as well established and how they address some limitations, and then and then I'll also talk about their own limitations, because that's also important. So Stateright is a model checker for distributed systems. It's actually a general purpose model checker, but it's tailored particularly for distributed systems. So model checker, Stateright is it's provided as a Rust library. Oops. So rather than being a piece of software that you run independently, you run it against your code, typically in a unit test or some scenario such as that. It allows you to verify systems that were implemented in the Rust programming language. That's what it specifically targets. One of the cool things about Stateright that I'll show later is that it includes a time travel debugger. So you might be familiar with reverse debuggers, where the debugger records a trace of how it got to a particular state, and so you can go backwards in time and explore sort of previous states on that particular trace. A time travel debugger lets you change your mind and explore other possible traces. So this is useful not only for debugging, but even for understanding algorithms, distributed system protocols, for example. It includes a model for actor system semantics. So this allows you to define your actor system using more familiar primitives, and then model check it without having to implement a model from scratch. It also includes a very simple runtime for the actor system. And so you can run your actors, for example, on a socket, doing UDP with encoding the messages with JSON or whatever other kind of serialization you want to use. It also includes code to help you define the reference semantics of your system. So you might say, my system behaves like a register. My system behaves like a map. My system behaves like a queue, etc. So that's really important. Is there a question? Okay. And then it also includes a built-in linearizability tester. So once you've indicated that my system behaves like a queue, you can then verify that that it actually adheres to that specification, so that it behaves like a true single-threaded queue. And I also spend quite a lot of time on documentation, so I think that's worth highlighting. So let's talk a little bit about what are the limitations here. So it does require access to your source code. It only supports Rust at this time, although supporting additional languages would be an interesting area to explore. The runtime is relatively simplistic at this point in time. It's not, I haven't done any sort of performance benchmarking, and frankly, I think I probably need to rewrite it. I just haven't had free time just yet to do that. It doesn't have a large community yet, and it will have breaking changes leading up to a 1.0 release. If you do plan to use this and breaking changes would be problematic, just reach out to me and I'd be happy to coordinate to make sure make sure those changes aren't too disruptive. These are some other systems that tackle the same sort of, they approach the problem in the same way that Stateright does, of letting you verify actual sort of production code. So I recommend taking a look at these as well. So now we'll actually jump into the code. This is going to be Rust code, and I will sort of I'll talk you through it. So even if you're not familiar with Rust, hopefully this isn't too unfamiliar. So we define something. Rust includes a trait, which you can think of as kind of like an interface for a model, and then your code would implement this model, this trait, I mean, or it would leverage a built-in model such as the actor model. There are two associated types associated with a model. There is the global state of the system that you're modeling at any given time, and there's also an action that indicates how does the system transition between states. So you can think of these associated types as being similar to generic type parameters, but they work in the other direction. So whereas a type parameter is an input for constructing a type, an associated type is an output. So given a particular type, it has a fixed sort of output type. And I'll give you an example of that in a moment. The initial states can be non-deterministic. So here a vec represents a collection of in this case, a collection of possible initial states. If the system is, sometimes a system will start with one initial state. It's like a deterministic start and then non-deterministic next state transitions. Here you indicate, given a state, so this middle parameter is a state, given a reference to a state, you have this output parameter where you collect all the possible output actions. So these are all the things that can happen next, given this particular state. This self parameter, I should have defined that earlier. That's effectively an immutable context. So, so any sort of configuration for your system or things like that, you can store that. You can access that from the self parameter. And then now you have the next state. So this takes the last state and it takes an action and it creates a resulting state. And this gets wrapped in an option type to indicate that it's possible that some actions are ignored. And so you can see that we're modeling our systems in terms of what you might call a transition system, which is like a state machine. And then the last thing that's worth highlighting on a model trait is the properties. So this might be things like the system is linearizable with respect to hue semantics, for example. So before we get into a distributed example, I'm actually going to do a kind of toy example that I think just helps illustrate the details of how of this how to implement this trait. So this is a sliding puzzle, and in the bottom right corner you see that there is a missing tile, so the 12 can go down or the 14 could go right. And the idea is that you jumble this and then you slide the tiles and you try to solve the puzzle. Now it turns out that somebody can pop the tiles out of the puzzle in some cases and create configurations that are not solvable simply by sliding. And so you might want to say a property of this game, or at least any game that I would want to play, any configuration that I would want to play, it should be the case that it is solvable. And so we're going to use our model checker to verify that property. Whoops. So here's the code. First, we define a puzzle. This is our configuration. So it takes an array of 9 unsigned 8-bit integers. 0 represents the empty space, and then 1 through 9 represent the actual tiles that you saw in this diagram here. In this case, we're just doing 3 by 3, not a 4 by 4. Then the actions here, you could slide a tile down, up, right, or left. It's sufficient to just indicate that you're sliding down. You don't have to say which you're sliding down, because you can infer that from what is empty, from what tile is what space is empty. So here we implement the model for this puzzle. So the state is simply a snapshot of a configuration. So that could be the initial configuration or a later configuration as you slide around the tiles. The action is sliding. And here are initial states. This is a deterministic start where we take the initial configuration and that will be the initial state of the system. Here we define the possible actions. So I will say in a real, perhaps in a more realistic model, you'll actually typically predicate the actions here. So you'll say, well, you can slide down as long as the tile below you is free. But it's for brevity, you can do that same predicate in the next state. And so that's what I'll do here. So here we go through the code. This first code computes the index of the position that is empty. So all we're doing is we're saying what tile has, or what index has value 0, and then that will be the empty index. And then we can compute coordinates. So the y coordinate and the x coordinate are relatively simple to compute. And then like I said, we earlier we didn't sort of verify, we didn't check to make sure that that sliding down is possible. And so that's done here. So if you ask if the action that's chosen is to slide down, and as long as the empty position y index is greater than 0, then the tile that you're sliding from is going to be 3 less than the index of the tile that you're sliding from is 3 less than where you're at, and so on. And then you've got and now based on where we're sliding from, we basically just swap the empty position with the tile that we're sliding from. And so you might then say, what are the here we define the property that says it should be possible that the puzzle is solvable. And so this is just a predicate that says at some point the state should be equal to the solved state. So if a configuration is not solvable, we can then put this into a unit test or something, or even just a its own program. And so we can define a particular configuration of the model. We can apply the checker method to create a model checker. This is a builder method, so or this returns a builder, so you can then sort of chain different properties, like how many threads do you want to use, etc. Then you indicate what kind of search you want to do. So in this case, we'll do a breadth first search that will find a minimal trace. And then join basically says, okay, if this is this is important for like a multi-threaded checking. So this basically synchronizes with the current thread and says, let me know when you're done checking, and then return. And then we can just do an assert property. So this will verify every property. If you have a property that is an always property, then if that ever doesn't hold, the model checker will fail the test. If you have a sometimes property, then if it doesn't hold at some point in the execution, it fails the test. And if you have an eventually property, then if it doesn't hold for every possible trace, it will fail the test. And if the puzzle is solvable, then your test would simply pass. You can even ask the checker to return a trace that gets you to any interesting discovery. So a discovery might be in a different system, it might be an invariant violation. In this case, it's a solution. And we can even encode those solutions into the tests if we want to. And in this case, it gives us a sequence of steps that solves that earlier configuration. So that example is, again, that's a toy example. Something that gets a little bit more into the real world is something that's, this is actually still being, this is a work in progress, but there's a library called Ibcrs. It is an implementation of the inter-blockchain communication protocol, which is a protocol for communicating between different blockchains. And this was developed by Informal Systems and is available on GitHub. And Vitor Enes Duarte ported a TLA plus model of that, or at least a subset, I should say, of the TLA plus model to Stateright to actually exercise the implementation. So just to kind of give you an example of how the code corresponds for people who are familiar with TLA plus, this shows you the top shows you the TLA plus code, and the bottom shows you the Rust code. Generally speaking, the Rust code's a little bit more verbose, but I think for this sort of example, they're about the same amount of complexity. So just as far as takeaways, this experiment was able to model check some of the Rust implementation. It's important to point out it's incomplete. It only ported a subset of the actions, and so far the property that's been checked is relatively trivial. But some takeaways here are that we were able to actually run the real system code, and the Stateright throughput happens to exceed TLC, which is the TLA plus checker. There's more performance comparison in the book if you're someone who uses TLC and you want to see or TLA plus and you want to see sort of how do the languages compare and how does the performance compare, just check out the book. And I think it's important to point out that Rust is definitely more verbose than TLA plus. It's more complex, so that is a trade-off. And also, Stateright is not as comprehensive as TLC, so there's quite a lot of additional functionality that TLC provides that Stateright doesn't yet provide. So now we'll dig into the actual the actor side of the framework. So here we have a trait that you implement to define your actor as a state machine. So you have two associated types, the message type that your actor operates upon, and then the internal state of the actor. And so the word state here is a little bit ambiguous. You can use state to refer to the state within the actor. You can use state to refer to the global state of the system, which includes, what are all of the actor states, but what also is the network state, and also things like, have actors set any timers. So that's state that you might not directly encode inside of this type, associated type. Actors are deterministic. So the start is going to, you define a method that returns the starting state. You have access to some context that you can specify for the actor, immutable context. You have access to the actor's own ID, which currently is computed based on the IP and socket that the actor is listening upon. And then you have this output type, which you can use to schedule timers or to send messages to other actors. And by the way, I should have mentioned, when I'm using actor here in the probably a more, or I should say a less formal sense. So actor systems in academia have a very sort of perhaps precise notion. This is basically a state machine that has access to immutable context, has access to its internal state, can send messages, can schedule timers, and that's, for the purposes of this talk, that's the definition of an actor. The next thing we define is what does the actor do when it receives a message? So here we have access to the existing state. This wrapper type is called a clone on write, and it's basically just an efficiency improvement, so that if the actor ignores a message, we don't have to mutate the state when we're doing model checking. Let's see, and here we have the source of the message itself, and then again we have access to this output type, so we can schedule a timeout, or we can send a message or send multiple messages. It's important to point out that the semantics here are that when you send a message, really what you're doing is you're indicating that a message is in queued for send. So even if you indicate I want to send a message and then I update my state, really the way that this gets captured by Stateright is first it's as if the state is mutated, and then it's as if the messages get sent. And similarly, what happens on timeout. And this has a default implementation, so you can omit it if you don't need to handle timeouts. And now we can get to an implementation of this. So here we have our configuration. So any particular actor may be the actor that's serving for this sort of ping pong example. And it needs to know to which actor does it serve to. And then we have messages. So there's a ping message and a pong message. Those include a count. And then the actor also has an internal state, which is the count that it last, or rather the count that it's expecting to see next. So the way that the actor starts is if this actor is an actor that should serve, which is serve in the sense of like tennis or ping pong, then it will send the ping message with the count of 0. And in any case, the actor will then return the state 0. When an actor receives a message, it matches on that message. So it's kind of like a switch statement. If the message is a Pong message and the actor's internal state matches the value in that message, then it will send a ping message. It will reply back to the source with a ping message that's one greater than the value that it received, and then it will increment its own internal state. And then conversely, the ping message, receiving a ping message does sort of the converse. So this is effectively the code that you would write. Then you also need to indicate what properties do you want to check from the system. And so you would use this built-in actor model struct to define that. So here, this struct has 3 parameters. One is the actor, one is a context. So things like, what's the maximum count that I want to count to during my model checking, and then also an optional history parameter. You indicate what are the initial actors of the system. And by the way, this is constructed with a builder, which again, to see that you can look at the book. So we have the actors that comprise the system, and this is not to be confused with the actor states. This is the actor, sort of the context themselves. The actor states are stored elsewhere. You have the configuration. This is made public because Stateright in your property, you can have access to your model, and so this allows you to get access to the configuration that you've associated with this model. You can indicate whether the network can duplicate messages. Most networks can. You indicate an initial history if you do have history, if you're recording history. You indicate the initial state of the network. It might just be empty. You indicate whether the network is lossy. So if I send a message, is it guaranteed to be delivered, or is the network free to in some sense, sort of delete the message so that it never gets delivered? You've got the properties that you want to define, and then it gives you hooks. So you can indicate when a message comes in, you can define a new history. That is, this is how you amend the history, given a previous history, and given a message envelope, which is a message, a source, and a destination. How do I amend the history to sort of record that? You might actually record the envelope itself, or you might record some sort of inference from that envelope. And then similarly for messages that come out of actors, and then you can define a boundary, which is the predicate indicating, what states are we actually checking for the purposes of this model checking. And this can access the configuration. So you can define your model once and then run it across different configurations, like different maximum counts, for example. So here we create a configuration for a ping pong system. Our configuration defines the maximum number sort of count here. We have a history type, which is the number of messages in and the number of messages out as a tuple. And then we can define a method to actually construct our model from that configuration. And you can see here the 3 type parameters for the model are the actor, the configuration, and the history. So we call this new method to instantiate a model. We pass in the configuration and we pass in the initial history. Then we can indicate each of the actors in the system. So we have one actor that is serving to ID 1. So when you're doing model checking, the IDs are dense and they start at 0. So this actor will have ID 0. This one will have ID 1. And then the second actor is not going to serve. When a message comes into an actor, we're going to increment its number of messages in, and similarly, we'll increment the number of messages out when a message leaves an actor. So this is how we're updating our history. The boundary is that we're going to model check up to the configuration maximum, the configured maximum value. And so now we can start to define some properties. So one property is an invariant, which is saying that the difference between the states of 2 actors should always be within 1. So the states might match, or they can deviate by up to 1. And so that's what this property is indicating. Another property you might say is it's the case that the system will eventually reach the maximum value. And this is true if the network will always deliver messages. So if the network is lossless, then you could show that this property is true. If the network can lose messages, then the model checker can actually falsify this property and show you a counterexample. For example, when the initial actor serves, that message gets dropped, and then the system basically just hangs and we never reach the max value. And then another property might be that the number of messages in will always be less than or equal to the number of messages out. If the network can duplicate messages, then this might not hold, but we actually baked into our implementation this check that the internal state matches the incoming message, which actually causes this to hold even if the message, or rather, even if the system duplicates messages. So now I'll move on to sort of the last slide about Stateright, which is, this is the UI, the time travel debugger. It's called Stateright Explorer. In the upper right corner, it shows you the status of the model checker. So what model are you checking? How many unique states have been generated? And is it done? If it's not done, it'll show you what it's currently, it'll give you a periodic snapshot of the trace of a trace that it recently visited. That can be useful if it's taking quite a long time and you're thinking, oh, maybe there's a bug in my model or in my implementation. And then you've got some discoveries. So in this case, I defined a property that it should be possible for a value to be chosen. A path is synonymous with a trace. It's a sequence of steps that gets me to where I am now in the system state space. At the top, you've got the current state of the system. Stateright has a way to let you summarize the state of a system so you don't have to look at everything. So in this case, I'm leveraging that to just give me sort of a delta. So it's saying, well, the last thing that happened is the actor sent a get okay message with message ID 8 and value B to actor 4. And then the internal state didn't change of that actor. But you can click this complete state checkbox to actually see the entire state of the system if you really need to dig into the details. And you can also define diagrams. So for the actor model, I've defined this diagram generator that will give you this sort of temporal diagram showing that a client sent a message to one of the servers. The server sent a message prepare to another server. That server replied. That gave us quorum for the prepare. So it sent a message to another server asking it to accept the value. And that server accepted, giving us quorum because we're also doing self-send. So this server is kind of processing its own messages, and so we've got 3 servers, and so 2 out of 3 gives us quorum. The server then replies to the client saying that the put was okay. It also broadcasts saying that a value was decided, and perhaps that gets delivered to another actor here, server 2, and then the client does a get and is able to get that value. So this is an implementation of single decree Paxos, for example. So as far as what's next, I'd really like to build a community. Right now, there's very few people sort of involved in the project, and I think it's ready to see a little bit more adoption. I'm working on this book. The next chapter is going to be on multi-Paxos, and then from there, I'm not really sort of undecided on what additional chapters to write. So if you have ideas, reach out to me. I would like to implement dynamic partial order reduction, which is a technique for pruning the state space. Basically allows you to check larger models in less time. The liveness checker right now, it has some limitations. So if the state space is cyclic, then basically it only works for acyclic state spaces. And then Tokyo and async standard are 2 very common sort of async network runtimes for the Rust programming language. And I think for people to actually use this library, I'll have to have a runtime at least for Tokyo, and possibly also for async standard. And then there's some things like maybe I can improve the ergonomics with generators. so that you don't have to explicitly manage quite as much state. I actually don't know if Rust will allow me to do this, and generators are currently an unstable feature of the language, but it's something worth looking into. Maybe adapters for additional languages so that you can model check other implementations at the cost of a little bit of model checking performance. And then any other suggestions, I'm open to suggestions, so I encourage folks to reach out. As far as resources, if you're familiar with the Rust programming language, RustDoc is sort of the standard for documenting your APIs. And so Stateright has pretty extensive RustDoc documentation. There's the book. The repository for the library has several code examples. And then there's a Discord for chat. So if there's any Q&A or just comments, that's a great place to go. So now my presentation is basically over. And so if there's any questions or if folks want to sort of see a live demo, we can do that.
Okay, maybe let's take a couple questions, then demo. What do you guys think?
Well,
so maybe
for the questions. I'm not sure we have time for the demo, to be honest. And the code was pretty, like the slides were pretty well organized for people to grasp the idea. At least that's my opinion.
So can you tell a bit about the architecture of this model checker? I mean, the context I'm asking is like this shows 2 orders of magnitudes improvement in performance with respect to TLA plus in one example at least. Like, where does that come from? Does that come from only from Java to Rust, or what are the clever things you are doing? What part of architectures contribute to that?
Okay. So as far as the architecture, the idea is that I fingerprint states. So I digest each of the states into a 64-bit integer. And this is an idea that I got this from a paper on the TLC model checker. But what I think Rust allows you to do that Java perhaps doesn't allow you to do quite as well is to densely pack information and not do quite as much pointer hopping. So I think that alone is probably one of the biggest contributors to the performance. Other contributors, performance has improved by sort of exploring different fingerprinting digest algorithms. And just generally speaking, since the very first implementation of the checker I wrote it to model check basically a graph of like integers. So a system that's basically just a set of integers evolving over an integer that sort of evolves over time. And I performance tested that. And with every single improvement, I do additional performance testing. And so I'm just very sensitive to any sort of performance regressions. And that means that the implementation has gone pretty slow, but it also means that if performance ever regresses, which it has at times, I can generally find out before I push that code to the master branch.
Okay. Mark, go ahead.
Rust is a pretty big language with things like unsized types and stuff like this. Are there limitations on the language that can be used for modeling? And the second question, I guess, is can you talk about what I came in a little bit late, but can you talk about what you plan to do with this model checker that made Rust a natural modeling language for you?
Sure. So to echo back, the first question was, does using a general purpose programming language introduce any limitations that perhaps you wouldn't run into with a special purpose programming language? Is that correct?
No, I just meant Rust is a huge language, and there are potentially some things that could slow down performance. Is there any aspect of Rust that I can't make use of when I'm modeling?
So there's nothing specific to the language that you can't use. Because I'm not parsing the Rust code. I'm actually truly running the Rust code. But as far as things to keep in mind, memory allocations, all those kinds of things do tend to slow down your checker. And so in some ways, when you're model checking your final production implementation, you will keep this, like, you'll just naturally think about that, and you'll say, oh, I could allocate this, but perhaps I don't have to do an allocation with every message. And so that in turn, I think, it puts a little bit of burden on the implementer, unless you just don't care, in which case it'll still work. But it frames your thinking, and in many ways, I think that can lead to systems that might actually perform better in a production scenario, because they're designed for performance with every step of the way. Does that answer your question, or did you want me to delve into a more specific aspect?
Well, that's fine. It just seems like it's very hard to take. It's very hard to model the state in a model checker if the state can grow arbitrarily. But
yes, that's very true. So you have to be very deliberate about the state that you're maintaining in your system. And again, this keeps things simple. So I would say that I don't want to bash on OO languages too much, but it's very easy to add lots of sort of abstraction and a lot of sort of additional state that's not really fundamental to solving the problem. And I think Rust does a pretty good job of guiding you, generally speaking, to be very sort of cognizant of the abstractions that you introduce. And at the same time, like when you're model checking a language, you also have to be even more cognizant of that, because introducing some auxiliary state that's not central to your model checking can increase the state space dramatically. And so it's just something you have to keep in mind. Thank you for those questions. Any additional questions?
Okay, Michelle?
Yeah, if I may. To me, the big limitation of model checking is it's not the speed at which you're going to model, it's the state explosion. That's when they kill you, right? So when we were starting with TLC here, we did some models, and then we said, let's try the fast model checker. So we redid the same models in spin with Promula. And that didn't change much of anything. It's just we would reach about the same limits, but faster, right? About the same model, but more quickly.
Right.
But it didn't get any further into the size of the model. So to me, the big limitation is the state explosion, and the way to deal with that is to be more abstract, right? That's how you reason on abstract models instead of the details of the implementation, and then you can handle the entire space because you have a more abstract space. And that's what I like about TLA, is that it allows me to write abstract things instead of low-level things. I hated Promula, right? I don't want to have to write everything like I'm in C. I was happy to write with quantifiers and sets, and so I'm not sure. You're more of on the side of Promula thing to me than more the side of TLC. I'm not sure this helps me much with the limitations that I find in TLC. So to me, to finish, because I go teach a class, but the big limitations I have with TLC that I would like other tools to address are two. One is if you try to deal with real-time properties, it becomes untractable very quickly. Even though Lamport says it's doable, it's in practice, it's super hard. And then the other thing that's even harder is anything that's probabilistic. So you have any idea on those things? Can you incorporate some probabilistic checking and some real-time checking? That would be a big advantage over the simpler model checker like TRC.
Sure. I think there's 4 topics to cover here. So Stateright doesn't force you to write code that actually runs in production. So you can write abstract models in Stateright, and the book gives some examples of that. So you're totally spot on. The state space explosion problem is a legitimate problem. Checking abstract models can be a good way to tackle the state space explosion problem. And so you can do an abstract model in either language. The speed is necessary but not sufficient. Or rather, raw speed is necessary but not sufficient is the way that I like to think about it. So there's a big difference between writing a model and then taking 5 minutes to model check it versus it taking 10 seconds to model check it in terms of your development velocity and your way to iterate and your ability to iterate on ideas. So again, while raw speed is not going to overcome the state space explosion problem, practically speaking, it can actually be the difference between a system that you find convenient and a system that you find so inconvenient that perhaps it doesn't see quite as much widespread adoption. as far as how to address the state space explosion problem while also checking real implementations and not just more abstract models, I think that's where dynamic partial order reduction is going to come in. That can reduce the state space orders of magnitude. And there's a lot of really great research there, and I just haven't had the cycles to implement that yet, but that's upcoming. And then as far as probabilistic, I have not yet explored that. It's kind of been in the back of my head, but I haven't really given it any thought.
Thank you.
You're welcome. Thank you for that question.
Anyone else?
I think we're willing to let model checkers run for hours, if not days. So the state space is a huge thing for us.
Yeah. I mean, there's cases where you're running, weeks or more than a week, 10 really beefy machines that are pretty expensive. I think there's two phases of model checking. Like there's when you're on your machine and just kind of sanity checking your model, and then you hand it to perhaps a fleet of servers to actually run a more exhaustive check. And in both of those cases, a 10x speed up is relevant because the difference between taking, like I said, in the seconds range, that also applies in the days range. Like being able to get feedback in one day that your model has a violation is great, is a lot better than it taking 10 days, especially when you've got like deadlines for releasing a product.
So in the beginning of the talk, you mentioned a few other systems that are like kind of similar in spirit, right? For different languages, I suppose. In what way Stateright is better? Like if there are existing systems, like what are you doing better to,
Yeah, it's a
to
great
warrant
question.
the existence of Stateright?
Right. I'll first be totally sort of open here and say that I developed Stateright out of a hunch that I think this would be kind of cool, and I wasn't aware of these systems. It was only when later on somebody reached out and was like, hey, have you looked at dynamic partial order reduction? I started reading the papers, and then I started saying, oh, wow, this is super well explored, and it's got decades of research behind it. So these other systems, some of them are faster because they've got dynamic partial order reduction that Stateright doesn't. What does Stateright do better? I would say the UI, I think, is relatively unique. I don't know how many of those other systems have like a time travel debugger where you can poke around and say, okay, find me an example where the system picks a value, and now let me sort of explore different ways, like different actions that can occur sort of near that state. But I'm not saying that to dissuade using those other systems. I think those other systems are super compelling as well.
Okay, any other questions from the audience?
Well, I'm curious to know, are there things that you can do using Rust as the modeling language that make this particularly exciting? For like, are there systems or problems you're trying to go after that you can do using Rust as the modeling language?
So I wouldn't say that there's anything that's unique to Rust, right? So any language could tackle these problems perhaps equally well. But as far as what I'm doing, generally consensus protocols is what I'm exploring, and the book is sort of a learning resource. So when you describe distributed systems to a person and you don't actually show them how the state can evolve, you don't have them write code, you don't flesh out the bugs immediately, I don't think that they learn as quickly as if you're explaining the concepts and then instantly showing them, here's a trivial implementation of a system that exhibits register semantics, or it should, and here's how it violates linearizability, and here's how we address that bug, but here's another problem. So that's sort of the way that the book tackles this problem, is it's incrementally teaching distributed systems in a sort of hands-on way. As far as what makes Rust a good choice, besides just performance, I do think it does sit in a sweet spot with regard to being able to write high performance systems or implementations while also being relatively succinct in a way that perhaps C might not necessarily be.
So any plans about parallelization of the model checker?
It's yeah, absolutely. So it is parallel. It can, on my machine, it'll peg all of the cores. I've got an 8-core machine, and I haven't tested it with sort of more cores. I also have not implemented distribution of the model checking at this point in time. My focus, with this is a spare project. I do this in sort of my spare time. So my focus has been what will it take so that to help teach distributed systems. And so focusing on local scenarios and making that as performant as possible and getting the documentation solid has been a bigger priority than how can I make model checking faster that, if I were to have 20 machines. But I do see that as obviously something that should be pursued later on.
I mean, does Rust, so you said that it has parallelism in the same machine. Does Rust have good framework to extend this to multiple machines because it's already has some parallelism in the same machine?
So I've actually played with the idea of using Stateright's actor framework to implement Stateright's distributed model checking. So, that's not unique to the language so much as just, given a library that lets you communicate across servers, you can sort of build upon that library. And I just thought it'd be kind of interesting to eat my own dog food, so to speak, and actually use the library. But I wouldn't necessarily use the checker to check the distributed. I don't know if there's, I haven't given too much thought to if there's interesting properties that I would actually model check there. But yeah, that's about as much thought as I've given to that.
So we do have a few questions in the chat.
Yes. So one of the questions is, you mentioned Ibcrs. Were they able to find any bugs so far using Stateright? No, this is very early work, and it's so no bugs so far. But I guess we'll see where that lands. And then some folks were asking about the book. So the book is available www.stateright.rs. It's freely available.
Okay. Yeah. You were mentioning one of the goals just recently you mentioned is like to teach the distributed systems, right? But like in my mind, if you're trying to teach distributed systems and like your second goal is to make them like runnable and the production ready, the two kind of they disjoint goals, right? If you want to teach something, you want to scale the problem down, think more abstractly. When you want to implement something, make it runnable, the scale is different, right? The approach is different, and also you have to maybe take your problems. Actually, most often you're not going to be like looking at one problem. You're going to have multiple problems, and you have to or components, and you compose them, and you probably want to double the model check how these components compose, and so on and so forth. So like a lot of complexity in the production, and the goal for teaching is to make things simpler. So I'm not sure I have a question, but like in my mind, it's two disjoint things, and you have one system to try to tackle both.
Right. I would say that first take a look at the book and kind of see how it presents the ideas, because it does start simple. The first thing it does is it says, okay, imagine you only have a single server in your system and one client. Is that, and the server persists, basically it's a register, it acts like a register, so put and get. Is that linearizable? And that's about as simple as you can get with a distributed system. And it shows that practically in a real system, it's not, because messages can be redelivered. So stale messages can be redelivered, and it incrementally builds from there. So I think you absolutely can start simple, and ultimately, you learn these techniques so that you can implement something. So why postpone that, right? By forcing you to implement something, you actually learn it better, I think, than if you had never implemented it. And that's the case, it's kind of like if you want to learn something, you try to teach it to somebody. If you want to learn something, try to teach it to a computer and see what happens. So yeah, I think you can start simple, and you can, and then the experiment here, and the thing that's unproven is, how far can you take it for something that's, real world, right? Could like for a really complex cloud service, could you really leverage this technique? And that's yet to be seen.
There is a question in Zoom chat. Would it be possible to support composition refinement in Stateright and the model checker? This is from Jonas.
Okay, that's a great question. So I believe so. Well, you can define the model semantics. So for example, so there's already some precedent for composition here. So you can indicate to the model checker that the network can redeliver messages, in which case it will retain messages indefinitely and then redeliver them at future points in time in the trace. But if you know that you have some sort of protocol that addresses the redelivery problem, then you can tell the model checker messages can't be redelivered because within the context of my system, due to the protocol that I'm building upon, I can take that as a given, and thereby perhaps prune the state space a little bit. But I do think that there's more that could be done with regard to composition, because having to sort of rewrite the model every time, or kind of update the model with each one of these different kinds of composable aspects, you shouldn't have to access the model source code, to the actor model source code, to do that. And so at some point, I probably need to look into like how to create more pluggable behaviors to make this sort of easier, but those will be based on real world scenarios. So as people reach out to me and as they say, hey, I ran into this and I really wish it worked that way, that will give me insight into, okay, that's a good place to focus my attention. Yeah, so, and then as far as refinement, that's also a super powerful technique. Certainly possible. It's not yet on my immediate to-do list, but if anybody's interested in submitting that to the project, it's freely available the project's available on GitHub, and I'd be thrilled to have additional contributors.
But traits seem like a natural path to doing abstraction. Replacing an implementation with an abstract model that has the same trait.
Right. Yeah. Exactly. So. But I haven't sorted out exactly what it would look like. But yes, it'd be a trait, perhaps on the actor model, and maybe that's a generic, or rather, maybe that's a concrete type, or maybe it's a dynamic indirection, so that you don't sort of. I'm starting to get into the weeds, but so that you don't make the external type too verbose. So by using a dyne in Rust, it sort of hides away the underlying plugins details, and so at the cost of perhaps a little bit of performance. And so there's a lot of decisions to be made there. But yeah, I think it would start with a trait.
John, this is super cool work. We didn't get I guess on Zoom we don't get a chance to applause or something, but this is super cool work. Okay. Thank you for the presentation. We can do the demo. I mean, for the people who wants to stick around for 10 minutes for the demo, I would love to see a demo. You have a video of a demo, but I think we can make it more interactive. If anybody has any questions during demo, we can ask.
Actually, I had a question. So have you thought about any way to like maybe check like Byzantine fault tolerance?
So I have never implemented a consensus protocol that is fault tolerant to Byzantine scenarios, but nothing prevents that. So
yes, yes, Jonas said like that was my kind of, that's why I didn't want to ask the question, because it's arbitrary behavior, but I would like to see something like some solution to that. Like that's how we dismiss like, hey, model checker, it's like totally arbitrary behavior, but there could be, I guess I would like to see some thought process on that side. Like how do we actually verify like Byzantine fault tolerance. Maybe in the process also like standardize sort of the definition, because right now it's like, hey, anything that is not crash fault tolerance is Byzantine, like it's not crash fault, but still like there could be some more guarantees that we can provide from the system. Like, hey, we have implemented this system. If your disk crashes, as long as like there is no adversary actively trying to like sabotage your system, until that, like we can provide these guarantees. We can provably provide these guarantees. So yeah.
But it would be done here exactly as you do it in TLA plus or Spin or Murphy. You just have you have a network model, some subset of the actions model the network, and you're off and running.
Right. So, there's different kinds of failures here. And, one failure is what happens if a node is compromised and it sends sort of these adversarial messages. And you can model that in Stateright today by saying that my actor type is an enumeration. It's either, a legitimate server, a compromised server, and then you would define the types of behaviors that you might expect from a compromised server, or it's a client, right? That would be those three types of actors in your system. And then similarly, Stateright doesn't yet have the actor framework doesn't yet have a notion of an actor crashing, restarting with stale state. That is definitely on my to-do list as well, and so on. So yeah, I totally agree with Mark. This could certainly be added.
Let's do the demo. And Vitor is also here. So Vitor did that work on the blockchain checking, right?
Yes. Hey, Vitor.
Hey, nice to finally meet you.
Yeah, it's great to meet you.
I've been talking with Jon for like months already, and asking questions about Stateright. Yeah, it's really fun, and I think one of the good things is the tooling. It doesn't exist tooling like that, at least for TLA, which is the other language I was using to model the system.
Yeah, that's great feedback. That was kind of the idea. Is I developed this based on, incrementally. I would say, I really wish that I could actually see the behavior trace. I really wish that I could see not just the global state of the entire system, but map the global state to like a concise summary. And as I ran into these kinds of like, I wish I had X, it was pretty easy to add those to the model checker because it's relatively small code base. So yeah, I'm really glad to hear that it's panning out for you as well. So if folks want, as far as a demo, I can show you a Paxos implementation or maybe ABD, and then maybe we introduce a bug and see if the model checker can find that.
Sounds good.
All right. Let's see. Okay. So here we've got a terminal. Is the text large enough for everyone to read?
Yep.
Okay, excellent. So here's the Stateright repository. There's an example, several examples here, and let's do the linearizable register example. So this uses this implements the sort of the ABD algorithm that I first learned from Murat's blog. And the idea here is that I guess I shouldn't take the time to sort of completely go over the algorithm, but here's an actor. It starts with the default value, and it broadcasts a query, and then it's let's see, where are we going to introduce a bug? Let's introduce a bug in the quorum portion. So first off, let me go ahead and actually check this.
Since Murat introduced the problem, Murat should introduce the bug, shouldn't he?
There you go. Let's see, this is linearizable register. thought I pre-compiled this before the talk. So first we'll run the, so I should say, let's look at what the unit test is saying. So it's saying that this linearizable register, in this case, we're actually saying if the network is not duplicating messages. So assuming that we have some protocol to prevent redeliveries, then the property should hold, and the properties that I am specifying are, actually, let me take a step back. I'm recording the history and I'm verifying that the history is actually linearizable. So this is like the property, and it's using the built-in linearizability tester. So let's see. Just want to run this one example. So it's saying that property does currently hold, and let's see if we can find somewhere that we're doing the quorum. So here we're saying that if I take the peers and I add 1, that gives me the total number of actors. And if I've reached a majority, that constitutes my quorum. So what if I had accidentally thought that my peers was just the was the set of all actors and not so that would be a pretty easy bug to make. So it indicates that a discovery was found. It says, well, for one, a value was not chosen. So hold on. So one of the properties that I defined is that a value should be choosable. Well, I'll go ahead and just demo that. So you might say, okay, actually, let me find something that would actually violate linearizability. Let's try to make it. If you can't choose a value, then you can't violate linearizability. So that's kind of trivial.
Oh, nice.
Hopefully this works. All right, let's see. How are we going to force this to violate linearizability? Insert.
Maybe don't do the repair phase if you are.
Oh yeah, that's a great idea. So we tell everybody to record this value. Then, okay, so the repair phase is where we ask everyone to record, and then, but if we don't do that, then we're not going to get back a quorum. So let's just start adding arbitrary. Let's like not set the sequencer. Let's see if that breaks linearizability. There we go. Okay, so it's telling me that it says, oh, you violated linearizability. Here's a trace that gets you there, and this is the sequence of messages that would get you there. And then it also gives you the final state of the entire system. And that might be a little bit counter. Like you might say, well, like I'm gonna have to debug this. This is tough. So you might want to use the UI here. Yeah. So let's go back to the test, and now I'm going to say that I want to run the test on port 3000. And so this is going to block the test. And now I can switch back to my web browser. And I will update, I'll have to change the share here so you can see what's going on in my web browser. So here, and let me, I hope this looks okay when I increase the text size.
Yep.
So here it says it generated this many states. It found 2 interesting discoveries. One is that a value is choosable, and it shows you this trace to get to a chosen value. But then perhaps the one that you really care about is a linearizability counter example. And in this case, I think I used depth first search. So this is not the shortest. Oh no, this is breadth first. And so what's going on here? So I probably don't want to debug this live, but it turns out that there's a sequence of steps where multiple values are chosen. First A, and then it looks like maybe Z gets chosen, but then I can return a stale value of A. And generally, what I've found is that these diagrams are a lot easier to debug than just reading the traces and trying to keep in mind, oh, when was this sent, right? Yeah, so that's kind of a demo. Is there any anything else I can demo at this point?
The visual is very cool. Every time I use TLA and I have a trace, I have to use a paper and a pen and a pencil to try to visualize stuff. So it's very nice.
But
right, yeah.
something to consider is being able to debug it in the context of the Rust code that defines the model. So, for example, we're model checking C code running in data centers, and we've now got the ability to take an error trace found by the model checker and run that and debug that trace inside Visual Studio. So just as if it's an ordinary. So you're looking at the error trace in Visual Studio just as if you were using an ordinary debugger. And so being able to relate this trace to the Rust code that you're using would be a neat. That's something I could easily imagine you doing, since you have such a beautiful trace here, being able to follow it through the code.
Right. In fact, you can set up breakpoints. So you could. I don't use a debugger for Rust very often, but I presume that you could set your debugger to when Rust panics. So when your invariant is violated, throw me into the debugger, and you can actually see sort of the internal state there.
Mm-hmm.
Yeah, that's probably something for me to play around with a little bit more, though, because yeah, I think that is definitely certainly useful if you've for non-trivial code to actually see, like, okay, what's some of the internal that's not
you have a beautiful representation here, because it encodes the source locations of the steps in your code just because you have the action names there, right there in the trace. So
right, yeah. For folks who, I guess I didn't really do a great job explaining this. So, I'm actually going to show you how this sort of pans out. So the initial state is there's only one initial state for the system. This shows you the entire system state. Here's the network. Here's each of the servers and their individual state and the client state. And then you basically pick what's the next thing that happens. Do you deliver A or do you deliver B? If you deliver A, what's the next thing that gets delivered? Maybe B gets delivered from a different client. And then you can sort of pan out the different histories. And this is the sort of time travel aspect that can be useful.